Hello everybody, welcome to my presentation. Today I am going to present a deep learning based Kalman filter for single channel speech enhancement. This is Sujan Kumar Rai. The other authors of the papers are Aaron Nicholson, Kuldeep Kepalial. We are from Signal Processing Laboratory, School of Engineering, Griffith University, Brisbane. Our paper ID is 1551. So here is the outlines of my presentation. In introduction, I will talk briefly about speech enhancement, then briefly review some existing speech enhancement methods, then Kalman filter for speech enhancement, then our proposed method, followed by experimental results and discussion, finally conclusion. Here you go, a single channel speech enhancement system. As can be seen, speech signal transferring through mobile phone or other communicating devices could be corrupted by surrounding noises, which could be crowd, vehicle, horn, engine sound, and make the speech signal noisy, which lose quality and intelligibility. Speech enhancement algorithm in this case can be used as a front-end tool to recover the clean speech, what we call enhanced speech. It could be used speech recognition, voice control autonomous system, etc. There are the existing speech enhancement system. Voice is Ball introduced 1997. The very first one is spectral subtraction. This is a widely used speech enhancement algorithm. However, it completely depends on noise power estimation. We see that if the noise gets under and overestimated, it produces musical noise and distortion in the enhanced space. We also compare our result with benchmark MMSE method as well as winner filter, where this method shows significant performance deficiency if the prior SNR is not estimated accurately. Then Kalman filter has been introduced 1987. This is also a classical signal processing technique, but it suffers from speech LPC parameter and noise variance estimation. Then deep learning, this is the forefront method for speech enhancement, which was initially used for estimating the time frequency masking of noisy speech, then estimate clean speech with the mask technique. However, if the mask estimation is not accurate, it may produce musical noise and distortion. So here in this paper, we focus on improving the Kalman filter for speech enhancement in various noise conditions by incorporating machine learning technique. Specifically, we utilize the noise variance and speech LPC estimates for the Kalman filter using deep learning technique. So here you go, a single channel speech enhancement using Kalman filter. As can be seen, equation 1 shows additive noise model where A is and B are clean speech and noise, and Y is noisy speech, and N is the sample index. It can be shown that in equation 2, speech signal is can be modeled by p-order autoregressive process, where AI are LPC coefficient, then represented in state space model, equation 3 and 4, as shown in 7, Palial and Bosu. So what Kalman filter do for each frame of noisy speech, give an MMSE estimate, which is represented by S at n given n, using 7 to 11 recursive equations, where bold letters represent vectors and matrices. The specifications are highlights there, 1 to 4 in this section. So estimated speech as sample n is given by equation 12. It can be seen here. The K naught n is the first component of Kalman gain corresponding to 9, represented by equation 13, where alpha square is a parameter as introduced in 20. So this method was initially introduced for enhancing stationary noise corrupted speech. So in this arrangement, we can see that the unknown parameters are linear prediction coefficients AI, the additive noise variance sigma square V, and variance of residual error sigma square W, what we need to estimate. So this is our proposed speech enhancements algorithm. As can be seen, we do framing with 50% overlap. For each frame, compute discrete Fourier transform, then construct magnitude spectrum of noisy speech. Then our machine learning based deep MMSE framework gives an estimate of noise PhD for each frame, for which we take square root, then multiply with the phase by applying inverse Fourier transform. It gives a frame-wise noise. From the frame-wise noise, we compute the whitening filter coefficient as well as noise variance. So the whitening filter coefficient then apply with the noisy speech to construct a whitening filter to, which gives a pre-whitened speech. and it reduces the noise effect significantly so that we compute the speech LPC parameters. Given the noise variance and speech LPC parameters, we construct Kalman filter and apply frame noise for each noisy speech. Then gives an estimate of clean speech. Apply overlap synthesis, we get estimated speech. So the goal is to estimate the unknown parameters, LPC and noise variance. First, we focus on noise variance estimate. To do this, equation 15 shows that we estimate the power of noise for each stem given the noisy speech power multiplied by a simplified version of MMSC equation, where the simplification is done by maximum likelihood estimate, setting a posterior SNR, prior SNR plus 1. In this arrangement, we see psi lm is a crucial parameter called a priori SNR, for which the estimation become accurate or not. To estimate this a priori SNR, we construct a variedic architecture of network as introduced in 24 use residual network. So given the noisy space, it gives a mapped version of priori SNR. So this is input layer and output layer. So between input and output, there is a series of residual blocks. So in this work, we have used 40 residual blocks. That means it contains 121 layers. It's a very, very deep architecture of neural network. So to maintain the flow of information, we use skip connection as represented by these arrow lines. What it is, it just add the output of each residual block to the input of next residual block, by which it maintains a flow of information from lower layer to upper layer during training. So each residual block, we see there are 3 convolution layers, where first parameter is the kernel size, second parameter is the output size, third one is dilation. In the residual block, the middle convolution layer contains causal convolution and dilation. In this case, since this is a very deep architecture, we have used cyclic dilation rate. That means 1 to 16. So this is an example as can be seen of dilation rate 4. So 1, it reaches residual block 3, dilation rate 4 is approaching. So when it goes to residual block 3, then dilation rate is start from 1. Dilation rate, what it does is an important feature nowadays. It increases receptive field artificially. That means more access of data to produce result in the next layer. So once getting a priori SNR, we compute noise estimate, then do inverse Fourier transform, give time domain noise, from where we compute noise variance using this formula in 16. Then construct whitening filter with the coefficient bk computed from this noise using equation 17 applied to the noisy space, which gives a whitened space, from where we compute the space LCC parameter. So for training, we have used 74,250 clean space, 2,382 noise recordings. 5% of these are used for validation purposes. All clean space and noise are single channel with sampling frequency of 16 kilohertz. We use cross entropy as the loss function with Adam optimizer. Gradients are clipped between -1 to 1. We have used 174 epochs and use a minibase size of 10, where this minibase component is generated by randomly select a clean space, a noise, as well as a SNR level from -10 dB to 20 dB in 1 dB increment. For testing, we have used noises database, which contains 30 sentences, 50 male, 50 female, with passing car and cafe bubble noises, where stimuli is corrected -5 dB to 15 dB in 5 dB increment. For evaluation, we use perceptual evaluation of speech quality, PESQ, and for objective intelligibility is quasi-stationary Smith transmission index. We also analyze the spectrogram. Then we show the subjective AV listening test result, where 5 listeners participate the test for a particular outer range SP05 corrected by 5 dB passing noise. Here we compare our proposed method with a KF ideal, where parameters are computed in ideal case. Then use some benchmark machine learning methods, ROI from processing of speech using fully convolution network, published IEEE transaction 2018. This is phase or deep neural network based speech enhancement, published 2019. Deep learning based Kalman filter. It is also published IEEE SCAS 2019. Then our proposed method. This is the performance result for bubble, cafe bubble and passing car as shown in PSQ A and B. Apart from KF ideal method, it shows that the proposed method shows consistent improvement from -5 dB to 15 dB for all competitive methods. If we compare the QSTA result, it shows that The proposed method is closely similar to the ideal method and bit improved than the benchmark method for all this passing curve and capable noise. This is the spectrogram analysis of the proposed method where typical send is SP05 corrected by 5 dB passing curve noise. So it can be seen that the enhanced speech contains less residual noise and background noise as compared to 3 existing machine learning which contains severe background noise as well as distortion apart from ideal method. That means our method did not contain any annoying sound. Informal listening test also confirm this. However, to validate our claim, we construct a massive A/B listening test where 5 listeners participate in the tests and we compare the result with other benchmark method as well as ideal method, clean speech and noisy speech as well, and take the average of the 5 people result and put the result here. So as can be seen, speech SP05 corrupted by 5 dB passing curve noise. The proposed method is preferred widely by the listeners, around 78% than that of more than 80% of AKF ideal method, but it produced better result than 3 existing best machine learning technique. This can be seen from here. Face your speech enhancement, then deep learning Kalman filter, raw from Kalman filter, followed by noisy speech and clean speech. So in this paper, we investigated deep learning based Kalman filter for speech enhancement. We construct a deep MMSE framework within residual network and temporal convolution network to estimate noise PhD, from where we compute additive noise variance. A whitening filter is also constructed with the coefficient computed from the estimated noise to pre-whiten the noisy speech prior to speech LPC estimate. The improvement of speech LPCs and noise variance enabled the KF to minimize the residual noise and distortion in the enhanced speech. The objective and subjective testing confirms that the proposed method outperforms the benchmark method in various noise conditions. These are the reference I have used in this paper 1 to 34, and some of the things are used for partial reference in this presentation. Thanks for your attention.